Alright, so we're going to start off with Chapter 2, Physics in Action, Newton's first law, a running start. The section starts off with talks of Galileo Galilei, the Italian physicist and astronomer, who had this thought experiment that if you had a pipe like that, and you neglected friction and everything else, then if you were to release a marble, that marble is going to go down, and then it's going to come back up and end right where it ended off, as long as it's smooth. And this would happen forever and ever. There's no loss of any energy or slowing down for any reason because it's a frictionless track. And then you can take that and put it on a flat surface and send it in some direction, and then the same thing would happen. As long as nothing changed and there was no friction, that ball would move on forever. Isaac Newton comes along and he takes these thought experiments and kind of formalizes them. And as he explains, the object's mass determines its inertia. So they're the same thing. Mass and inertia are the same thing. And he develops his first law of motion. So Newton's first law of motion. Hold on.
Thank you.
I almost forgot. So you're going to go pick them up?
Yes. Either this afternoon or tomorrow morning.
Yep, thank you. Sorry. So Newton's first law of motion says that an object in motion or at rest will stay either in motion or at rest until an unbalanced force comes along and acts on it. Motion or at rest until an unbalanced force. Okay, so that should lead to your question, what is an unbalanced force? We've talked about it already this year, but if you need a refresher, if we picture an object just sitting on the ground, then the forces acting on it, of course, gravity, the force of gravity, and the floor is keeping it in place. And we call that the normal force. Though that is a balanced situation. If we leave that box there one day and come back a million years later, that box will still be there unless something comes along to change its state of motion. So if somebody comes along with their foot and they kick the box, now we have an unbalanced force. So the force of somebody's kick, the kick force, it's unbalanced. We can see the normal force and the force of gravity cancel each other out. There's nothing on the right side to cancel our kick force out. So that must mean there's a total change in motion. And for a change in motion, there has to be a force. And Newton's second law is just force equals mass, some mass, times an acceleration. If you're changing the state of motion of that box, then you are accelerating it, either speeding it up or slowing it down. So this is Newton's second law. And before we go on to the third in the reading, there's a test your understanding. It says to determine which of the following carts has the greatest inertia. The first one is a 1 kilogram cart moving at 5 meters per second. Second is a 2 kilogram cart moving at 3 meters per second. Third is a 3 kilogram cart moving at 1 meter per second. And the last one is a 4 kilogram cart moving at just 1 meter per second. Now, depending on how in-depth you read, you may be tempted to just say, okay, 5 times 1, so this will have a total of 5. 2 times 3 is 6. 3 times 1 is 3. 4 times 1, where's my calculator? 4. So you say, it's got to be this one. But no, that's not accurate at all. Instead, earlier, we defined inertia as mass. So which of these carts has the greatest inertia? Which one has the greatest mass? It's that one. Then it goes on to talk about SI units. The SI units that we're dealing with here for mass, everything should always be measured in kilograms. And this is just a standard unit for mass that's used around the world. Running starts. All right, so the next section talks about running starts, and this happens in sports all over the place. I think about baseball and an outfielder running up, scooping up a baseball, doing a little hop, and launching the ball towards home plate to get a runner out. But as mentioned in the section, it could be a javelin, it could be football, the quarterback leaving the pocket and running up and then launching the ball. By doing that, or a runner, you can do this yourself. If you jump and then if you stand in one place and then jump and then measure your height and then you run and jump, when you run and jump, you're going to go a lot farther. And that's because your velocity in this direction is going to be built up as you're moving along here. For the example used in the book, the girl launching the javelin speed after it's launched is just the speed of her hand plus the speed of her elbow. All of these little speeds added together, plus the shoulder, plus her body, all of these speeds added together will give her a faster speed in the javelin throw, which means that she's going to be able to throw it farther. So if she were training to be a javelin thrower, which some of you may be, don't forget your cardio. Don't forget to do some sprints. Build up that speed. Then it talks about acceleration. Acceleration is just your change in velocity over your change in time. So as your speed changes, as time goes on, you are accelerating. You could have an acceleration that is positive or negative. If you have a negative acceleration, say 3 meters per second squared, then that does not mean you're slowing down 3 meters per second every second. Instead, it means that you are just accelerating in the opposite direction. That's all that negative sign means. Let's talk a word about the units here. So we said acceleration is a change in velocity over the change in time. Acceleration, the units for velocity are meters per second divided by seconds. So this becomes acceleration is meters per second every second. So every second that goes by, your speed is changing by this much. That's what acceleration is. Another way to write this is just saying meters per second squared. And that's because a meter per second is the same thing as a meter per second times the inverse of a second, which becomes meters per second squared. That is your unit for acceleration. Next, frames of reference. Frames of reference are useful in determining speeds for problems, especially where there's relative motion. So depending on your frame of reference when looking at a situation, things could be changing. So if we imagine you're sitting in a car and looking at the person driving you, steering wheel, sad face because they're driving down Blanding. So you're staring at this person. To you, if you neglect everything that's happening in the background, which is hard to do, so to you, then that person does not look like they're moving. But the second you take into consideration the trees in the background, then you can see relative to those trees, that person is not moving. They're stuck in traffic. So let's say traffic's over. Now we've got the smiley face going. And all of this becomes a blur. And green. So these trees lose their shape and they just become blurred, and there's not a whole lot you can actually make out. Now, to you, that driver relative to the trees is moving in this direction.
I'm feeling food today. Thursday.
Mm-hmm.
I don't know.
So relative to those trees, you can tell that this person is moving. It's hard to do this when you're in the car. You kind of really have to focus in on that person's face, but it is possible to do. Just stare them right in the face, and inside your body recognizes that you're moving, you're being accelerated, or moving at a constant speed, but just think about what you are seeing, because that's important. When we're doing physics problems, there is no feelings involved. It's just what we see. Then we go into Einstein's special theory of relativity, which is based on two postulates. First one is that no matter what your frame of reference is, physics still exists as physics. So for special theory of relativity, frames of reference equal physics is how I would phrase that. And the second one says that the measured speed of light is identical for all observers, always. This is something really cool. Nothing we're going to deal with mathematically, that's advanced physics stuff, but say you are on a spaceship, a rocket ship. You're on a rocket ship, and you have found a way to go the speed of light. The speed of light is really, really fast. It's 3e8 meters per second. So 3 times 10 to the 8th meters per second. That's just me being lazy. Sorry. 3 times 10 to the 8th meters per second. That is 3, 2, 3, 4, 5, 6, 7, 8 zeros. That many meters every second. And there's your commas for reference. So you're going that fast. At this point, just like in Star Wars, light is not moving anymore. These lines, what you see in Star Wars as they're in warp drive, going the speed of light, that is the light being stretched out. Because as you're moving that fast, light behaves the same. Physics still happens no matter your frame of reference, but instead the light is now stretched out into these long lines. So one popular thought experiment is, okay, so you're moving at the speed of light. What if you try to turn on your headlights? How fast will the speed of light be going? Well, we learned that Javelin's velocity was due to her running start, the velocity of her body plus velocity of her hand and all of that. So should we take the velocity of the rocket plus the velocity of light and add them together to get this like new twice the speed of light thing here? Well, no. We can't do that because physics always works no matter your frame of reference. So the speed of light will always be the speed of light. If you're on a rocket ship going the speed of light and you try to turn on your headlights, there will be no speed of light. There will be no light emitted because you're already going the speed of light.